Okay, this is part 3, solving quadratic trig equations, and what we have here in our first example is an equation that doesn't even look quadratic, it just has a bunch of trig functions in it. We're going to solve this one just by using the identities and writing everything in terms of sine or cos. When you have multiple different functions in a trig equation, it's always, valuable to write them in terms of sine or cos. It's much easier to solve something if you have it written in a common language. When you have multiple functions, you'd have to graph sine times secant times cotan, and that graph, the resulting graph, is challenging to figure out what it's going to look like without doing any math. Same with sine times secant. So we're going to do a little bit of math here to kind of try to simplify. So let's write everything in terms of sine or cos and see what we've got, really. So sine is already in terms of sine or cos. So I'm going to write sine x. Secant, that's just 1 over cos. And cotan is just cos over sine. On our right side, sine is sine. And secant is just 1 over cos. So now we're going to simplify and see what we've really got here. Well, sine times 1 is sine over cos is sine over cos. And sine times cos would be sine cos over cos x sine x. And sine divided by sine is 1, cos divided by cos is 1, so our left side simplifies to 1. Sine times 1 is sine over cos. And sine over cos, well, that's just tan. So to solve this equation, really we're just looking for where tan is 1. Well, tan is positive, according to the cast rule, in quadrants 1 and in quadrant 3. And if we do tan inverse, we'll get our reference angle. Tan inverse of 1 is pi over 4. So we need answers in quadrant 1 and quadrant 3. Our reference angle is pi over 4, so that means we're going to have an angle here. And in quadrant 3, our angle is going to be here. So there's our Q1. This is our Q3. So our reference angles in both cases is pi over 4. So our answer from quadrant 1 for x is just pi over 4 because beta is theta in quadrant 1. And in quadrant 2 or 3, it would be pi plus pi over 4, which would be 5 pi over 4. So we were able to solve this trig equation just by using identities, simplifying, and solving. Did it turn out to be quadratic? No. No, it didn't. But from the original, it could have been. But through some simplifying, we ended up with just a linear trig equation that we were able to solve. Now our last example, example 4, is definitely quadratic. We can see it right from the beginning. Sine squared x is one of our first terms. So we've got 2 sine squared x minus 3 sine x plus 1 equals 0. This, very similarly to our first example that we did in our second video, was areas that we have a squared term very visible right from the beginning. What makes it different is that we also have this x term. So we have 2 terms. So we can't just isolate for x by isolating for sine squared x and taking the square root because we have this sine x term. So what we have to actually do is we have to factor. And why do we have to factor? Well, if I say let sine squared x be x, this might look more familiar. This would say 2x squared minus 3x plus 1 equals 0. And we know how to factor that. In fact, we can factor that. We're looking for numbers that multiply to 2 and add to negative 3. And that'd be negative 2 and negative 1. So to factor, we would say decompose or split that middle term into negative 2x and negative x. And then we would group and common factor. Well, common to the first 2 terms is 2x. And then left over would be x minus 1. Common to these first 2 terms, since negatives at the beginning, is we have to common factor a negative. And that would give us negative, or x minus 1 in that bracket as well. Now we have a common binomial term, x minus 1, our common bracket. So our first factor is x minus 1, and what we're left with is 2x minus x minus 1 divided by x minus 1 is 1. And at the very beginning, we said let x be sine x. So what we have is sine x minus 1 and 2 sine x minus 1 equals 0. And now to solve this, we take each of these brackets and set them equal to 0 and solve. So we're looking for where sine x minus 1 equals 0 and where 2 sine x minus 1 equals 0. And basically we're just solving two linear equations, and both sets of solutions will be solutions for our equation. Now, if you don't want to use the variable substitution, you don't have to. You can look at this and visually think, well, this sine squared x is like just x squared, and this sine x is just like x. So when I see this, I got a squared, an x, and a constant. So I'm going to factor it like a quadratic. In this case, a complex quadratic, because the a value is not 1. So I'm going to factor just like I factored our other example. I'm going to say do 2 times 1 gives me 2, and I'm going to see what multiplies to 2 and adds to negative 3. Same thing as we just discussed. That would be negative 2 and negative 1. So we've got negative 2 sine x and negative sine x. And those together would make our negative 3 sine x plus 1 equals 0. Now I'm going to group these two terms in common factor. What's common to these two terms? 2 and sine x. What's left over? Sine x and minus 1. What's common to these two terms? We have a leading negative, so negative 1 is common. And that leaves us with sine x minus 1. Now we have a common binomial term. So we'll common factor that common binomial term, sine x minus 1. And what we're left with is 2 sine x minus 1. Now, it's up to you which way you use. If you don't make the variable replacement, you can do it in 3 steps. If you do make the variable replacement, a couple more steps, or actually just one extra step. It's up to you what method you want to use to solve. Make the replacement and then substitute it back at the beginning or at the very end, or do the substitution right away. And then to solve this, to make an expression of two factors equal 0, it's when either of the factors equals 0. So it's when sine x minus 1 equals 0, or when 2 sine x minus 1 equals 0. And now we can start solving. Well, that's when sine x equals 1, or this one is when sine x equals 1/2. Well, sine x equals 1 is a critical value. If we think about the graph of sine, sine starts here, goes up, reaches a maximum, goes back down to 0, down to negative 1, and back to 0. That maximum right there is when sine x equals 1. And that maximum occurs at pi over 2. So your only solution from 0 to 2 pi for when sine x equals 1 is pi over 2. So for sine x equals 1, x in this case is pi over 2. And that's your first answer. To solve when sine x equals 1/2, you're going to have answers in quadrant 1 and quadrant 2 because sine x is positive, and according to the cast rule, that's when sine is positive. If you do sine inverse of that fraction, or if you use your special triangles, this triangle has the 1 and the 2. Sine is opposite over hypotenuse, so sine of pi over 6 is 1 over 2. So we've got pi over 6 in quadrants 1 and 2. So if I graph it, it means we're going to have an answer here where our beta is pi over 6. And since we're in quadrant 1, beta and theta are the same, so that means our x2 is pi over 6. That's our quadrant 1 answer. Our quadrant 2 answer, your beta is still pi over 6, but when you're in quadrant 2, your answer is pi minus pi over 6, which would be 5 pi over 6. That which is this angle. So our x1 in quadrant 1 is just our pi over 6, so our x2. And our x3 is in quadrant 2, which is pi minus pi over 6, or 5 pi over 6. So, quadratic trig equation. Use a variable substitution or not, up to you. Factor, complex trinomial, and then solve each factor equal to 0. And you're just solving two linear equations. For practice, try practice 3. It looks intimidating because there's a cube, but if you look at each term, sine x cubed, sine x squared, and sine x. Each term has a common sine x. So you can start by common factoring, and then you're left with a quadratic. If you want to do variable substitution at the beginning, go for it. Just make sure you substitute back at the end before you start solving, or else you'll not end up with correct answers. You'll end up with values that solve a quadratic, not values that solve a trig quadratic. But try practice 3, check the solutions, and then we'll do a warm-up tomorrow in class and go from there. Thanks for watching, and that's it for Unit 7, actually. So I'll see you in Unit 8.